Welcome back, everybody. In this video, we will be covering the first part of Lecture 13. The topic is the multi-period binomial model. We will split the lecture into 3 videos. In the first video, we will discuss the 2-period binomial model. Previously, in lectures 11 and 12, we worked with a 1-period binomial model. We will now add an additional period to this model and do our pricing formulas. In the second video, we will discuss the general n-period binomial model. Here, n can be any positive integer, and we'll generalize and we'll compute the formulas for pricing, call, and put options. And in the final video, we will discuss American options and pricing on the binomial tree. Okay, let's get started. Our setup is as follows. There's a non-dividend paying stock S. The stock's price today is S0, and its payoff in the future is random, and it's unknown as of time 0. The continuously compounded risk-free interest rate is R. It's greater than or equal to 0. And now, in this 2-period binomial model, we have 3 equally spaced dates: 0, little t, and capital T. And so on the timeline, they look as follows. There's 0, there's little t, and then there's capital T, where the distance between little t and capital T is the same as the distance between 0 and t. Okay. These dates correspond to 2 different periods. The first period corresponds or spans the period from 0 to t. The second period spans the length of time from little t to capital T. The second period is new. We have not worked with this before. Previously, we only had one period in which there was 0 and cap T. We now have an intermediate date in this model. We assume that at the end of the first period, at date little t, there are going to be 2 possible states. So first, there is a U or an up state. Second, there is a D or a down state. So at time 0, we can go either up or down. Next is date little t. There's either the U state or the down state. Okay. In the U or the up state, the stock has a price of SU equal to U times S0. Here again, SU is just equal to the gross rate of return on the stock between dates 0 and little t in the up state. And in the down state, the price of the stock is SD. It's equal to D dot S0, where the D is the gross rate of return over the time period in state D. Okay. There's nothing different between here, this step 4 right here, and our previous 1-period model, except now we have date little t here instead of date capital T. The big change is what happens at date capital T. At the end of the first period, date little t, there's 2 possible states. And at the end of the second period, date capital T, there's 4 possible states. So you have date 0 to begin with. Things can either move up or down. Date 0, date little t, date capital T. There's either U or D at state little t. And then at state capital T, there's 4 possible states. First, there's an up state called UU. Second, there's a down state called UD. Third, there's a down-up state called DU. And fourth, there's a down state called DD. Okay. In the up state, the price of the stock is then assumed to be called SUU. It's equal to the gross rate of return squared whenever there's an up movement times S0. In the up-down state, the price of the stock is denoted SUD. It's equal to U times D, dot S0, up times down times S0. In the down up state, the price of the stock is SDU. It's equal to D dot U dot S0. Note this is the same exact price as SUD, okay, because it's multiplication. You can just reverse the terms. And finally, in state SDD, the price of the stock is SDD equal to D squared, or D times D times S0. Okay, so that seems like a lot to remember. Okay, there's two possible states at date little t. There's state D, which the stock price is SD. There's state U, where the stock price is SU. And at date capital T, there's four possible states: up, 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 down, up, and down, down. So a lot to remember, but actually the model is really simple. Okay, think of it this way. In each period, the economy can either move up or down. If the economy moves up, the stock price changes by a factor of U. And if the economy moves down, the stock price changes by a factor of D. This assumption gives us two possible states at date little t, up and down, and four possible states at date capital T, up, 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 down, up, and down, down. Finally, for mathematical convenience, we're going to just assume that gross returns satisfy the following equation: U dot D equals 1, or equivalently that D is just equal to 1 over U. So no real reason to do this. It's just to simplify everything mathematically. Okay. And what we want to do in this model is we want to go out and we eventually want to price a derivative X with general payoffs X capital T. And these payoffs vary by the states. So there'll be an XUU payoff, an XUD payoff, an XDU payoff, and an XDD. We're going to want to price this derivative using similar techniques we had before, but now accounting for more possibilities at the terminal date. This slide is a summary of the model, very similar to the diagram I drew on the last slide. We have three dates: 0, little t, and date capital T. There's two periods, okay? The first one spans 0 to little t. The second period spans date little t to capital T. We have two basis assets, the stock and the bond. The price of the stock is known, it's given us today, it's S0. The price of the bond is just the discount factor, e to the negative RT. The payoff occurs at time capital T, make a note of that. In each period, like we said, the economy can either move up or down. If the economy moves up, the stock price changes by a factor of U. If the economy moves down, the stock price changes by a factor of D. This setup gives us two possible states at date little t. First, there's an up movement. In the up state, the stock price is equal to SU, equal to U dot S0. Okay. And in this D state, okay, if the stock price moves down, or if the economy moves down, the stock price is equal to S sub little d. Okay. At this intermediate date, little t, the price of the stock or the economy can either move up or down again. We said at each date the economy moves up or down. Suppose we start in the U state at date little t, then the economy can move up again. This state is called UU. Or the economy can move down given that we're in state U already, UD. Okay? In the up state, the payoff to the stock is SUU. Whenever there's an up movement, the stock price increases by U. So SUU is U squared equal times S0, or equivalently you can think of it as SU dot U, and this just breaks down to U dot U at S0. Okay? In the UD state, the stock price is SUD. We know if the economy moves down, the stock price changes by a factor of D. Previously, at the start of this period, the stock price is SU, moves down, so it gets multiplied by D. So it's nothing more than U dot D times S0. Okay. If we start in the down state, then the economy can either move up or down as well. If it moves up, we're in the state DU. If it moves down, we're in state DD. The stock price in state SDU is equal to D.U.S0. It starts at SD, okay, right over there. It gets multiplied by U, which is just D.U.S0. And similarly for SDD as well, right? So it starts at SD.D, nothing more than D squared S0. Okay, the bonds payoff B is 1 in every state. We assume it gets paid at date capital T. We could change it to whatever we want. And again, the price of the bond is just a discount factor. Ultimately, our goal is going to be to calculate the price of a derivative X, X0. We'll show it in the next slide. The derivative's payoffs are only going to occur at date capital T, not at the intermediate date. And they're also going to depend on the state, as we'll show in about 2 slides from now. There'll be an XUU, an XUD, an XDU, and an XDD. Okay. So how do we go about pricing this derivative, which is going to be our goal? Always, 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 the easiest tool to use is the F-tap. Okay, so to price the derivative X, we'll use the F-tap. And the fundamental theorem of asset pricing, or the F-tap, states that the price of this derivative X is just its discounted expected payoff under the risk-neutral measure. The payoff occurs at time capital T, so we discount by the risk-free rate back to date 0 from capital T, and we take the risk-neutral expectation of this payoff. Okay? The key term that we need to calculate is this expectation here. So we write key term to calculate. Okay. Recall always that the expectation is always just the weighted average payoff of the derivative, where the weights are risk-neutral probabilities. The only difference now is that we're going to have more than 2 risk-neutral probabilities. We're going to have risk-neutral probabilities corresponding to every state. Specifically, we're going to have 4 states at date capital T. We'll have state UU, UD, DU, and DD. The payoffs in these states are going to be XUU, XUD, XDU, XDD. And then what we do to calculate the weighted average payoffs, we just somehow, we'll see in the next slide how to do this, compute the risk-neutral probabilities of each of these states. QUU, QUD, QDU, QDD, such that this is a probability measure. So QUU plus QUD plus QDU plus QDD is equal to 1. Gives us this weighted average. Multiply and sum these up, we're going to get this expectation, okay, and discounting at the risk-free rate is going to give the derivative price. This slide summarizes the risk-neutral probabilities and the derivative payoffs. Again, just like in 2 slides ago, we have 3 dates and 2 periods, okay. In period 1, the economy can either move up or down. What we want to do is we want to compute the risk-neutral probability of this up move. The risk-neutral probability up move is going to be the same exact formula we had before, except you just substitute little t in for where big T was. Risk-neutral probability of the up move is just e to the RT, little t, minus d over u minus d. Look back on lecture 12 slides, you'll see that this is almost exactly the same, except we're using little t here. Risk-neutral probability of a down move, again, probabilities must sum to 1 at every time, so it's just 1 minus QU. Okay. It turns out that since we're using the same length of time between each of the states, and the stock can move up or down by the same multiplicative factor each state, the risk-neutral probability changes are going to be the same every time, or at least conditionally. Okay, so if you want to go out and you want to calculate the probability of the UU state, all you need to do is calculate the probability of the stock moving up 2 times in a row, assuming that these events are independent. So all you do to calculate the risk-neutral probability of, say, the up state is you take the probability of moving up once, which is QU, and you multiply it again by QU again. So once you're in state U, the probability of moving up again is QU. Probability of moving down is 1 minus QU. And to get that probability from the standpoint of date 0, this is a conditional probability at state U. To get the unconditional probability at date 0, you multiply them together. Okay. So to recap here, what happens is essentially the economy can move either up or down in each period. The risk neutral probability of moving up in each period is QU. The risk neutral probability of moving down each period is 1 minus QU. The probability of moving to the up state to begin with is QU. Probability of moving to the down state to begin with is QD, 1 minus QU. There's 4 states at the end. The risk neutral probability of being in the up state is QUU, equal to QU squared. Risk neutral probability of being in the UD state is equal to QU times QD, or 1 minus QU. Risk neutral probability in being in the down up state is equal to the probability of getting to the down state in the first place, QD, times the probability of an up move, QU. So it's equal to 1 minus QD, 1 minus QU times QU. And then the probability of moving to the DD state is the probability of getting 2 consecutive down movements in a row. Probability of getting 1 down movement is 1 minus QU. Probability of getting another one on top of that is you multiply by 1 minus QU again. So it's 1 minus QU squared, or QD squared. Okay. Again, the derivatives payoffs all occur at date capital T, and they depend on the state of the world. In the up state, the derivatives payoff is XUU. In the down state, the derivatives payoff is XUD, XDU, and XDD. Then when you want to compute the derivative price, what do? You just take all these payoffs and you weight them by their risk neutral probabilities. So really the computational task becomes very simple. All you need to do is you need to go out and calculate the risk neutral probability of a single up movement. This is going to be sufficient to give you the probabilities of all the terminal states. Then what you need to do is go calculate out all the terminal payoffs of the derivative across all the states, then weight them all up and you can get the derivative price no problem. So that's a lot of take in theory-wise. Best way to learn it better is to do a practice problem. I'll give you a minute to read the question and then I'll solve it out. Okay, so I'll read the problem statement, follow along with me, and then we'll solve. We have Microsoft stock, okay, and Microsoft is a non-dividend paying stock. Today's price of Microsoft is $100 per share, and we have 3 dates and 2 periods. We have date 0, 1, and 2. Date 0 is date 0. Date 1 is equal to date little t. Date 2 is equal to date capital T. We have 2 periods. The first period spans from 0 to 1. The second period spans from 1 to 2. In each year, the Microsoft stock can either move up or down. If it moves up, then it gets multiplied by a factor of 2, or the gross rate of return is 2. If it moves down, the gross rate of return is D, equal to 1/2, which is equal to 1 over U. Okay. The continuously compounded risk-free interest rate is 0%. Assume there's no arbitrage. And we want to price a call option, European call option on Microsoft with a strike of 100 and a maturity of 2 years, corresponding to date capital T. To do this, we're going to answer 3 sub-questions. First, what are the payoffs to this call option at date 2, the terminal state? What are the risk-neutral probabilities? And then take this weighted average, discount it back, and find the price of the call option today. Okay. So let's start by drawing our binomial tree. We're going to do this for instructive purposes. There's going to be 3 dates: date 0, date little t, and date capital T. Might have to adjust where these are positioned. Okay. At date 0, there's a single node. Everything is known. Okay. And in each period, the stock price can either move up or down, or the economy can. Okay. So in the first period, it either ends up or down. So this is the U or the D state. And conditional on being in either of these states, the economy can either move up or down again. Okay, so if you're in the up state, the stock or the economy can move up again, which is going to leave you in state UU. It can also move down, which will leave you in state UD. If you're in the down state, it can either move up, which is going to leave you in state DU, or it can move down, which is going to leave you in state DD. Okay, I'll adjust that over there. There are 3 assets that we're interested in: the stock, the bond, and the call. The stock has a price of S0 equal to 100 today. The bond has a price of E to the negative R capital T. Let me erase that. B0 equal to E to the negative R capital T. Capital T is 2 here, times little t is 1 here. E to the negative 0.00 times 2, which is just 1. Okay. Call price, which is what we're going to solve for, is unknown as of date 0. That's what we want to calculate. The payoffs to the stock are as follows. Okay. In state U, the price of the stock is SU equal to 100 times U. U is equal to 2, so it's equal to 200. In state D, the stock price is equal to SD equal to 100 times D, which is 1/2, which is 50. In state UU, the stock price has moved up twice, so SUU is equal to U squared dot S0, or 2 squared dot 100, which is 400. In state UD, it's equal to SUD equal to U dot D dot S0 equal to 2 times 1/2 times 100, which is just 100. In state DU, the stock price SDU is equal to D dot U dot S0. Okay, it's equal to 1/2 times 2 times 100, which is just 100. And in state DD, the stock price has moved down twice. At the intermediate date, little t, it's equal to 50. It's going to move down again by a factor of 1/2. Again, once it's at 50, so it's equal to 1/2 squared times 100, which is equal to 25. Okay. The bond has a payoff of 1 in each terminal state and it accrues no interest. So at BU equals to 1, BD equals 1, and BUU equal to 1, BUD is equal to 1, BDU is equal to 1, and BDD is equal to 1 as well. The risk-free rate is 0. In the first part of the question, we want to calculate the payoffs to a call option. The call option has a strike of K equal to 100. Okay, and so it's at the money, and we want to calculate its payoffs in each of the terminal states. The way you do this is just by writing it down. The call's payoff depends on the stock's price at the later date. We know what the stock prices are at the later date. In the up state, it's 400. Up down state and down up state, it's 100. And in the down state, it's 25. All we have to do is calculate or apply the call payoff formula in each of these states. So we'll start with C. We'll write them all down that we need to calculate. Okay, so we're going to need to calculate CUU, CUD, CDU, and CDD. CUU is max of the stock price, SUU, minus the strike, K, equal to 0, and 0. Plug in inputs, max, stock price in this state is 400, strike is 100 given in the problem. It's max of 300 and 0, it's just 300. In state UD, it's equal to the max of SUD minus K in 0. SUD is 100. You can see it in the binomial tree. Minus strike 100 and 0. This is just equal to 0. The stock price in the down-up state is the same as the up-down state, so the payoff to the call will be the same. It'll also be 0. And in the down-down state, it's going to be max SDD 25 minus 100 and 0, which is going to be 0 as well. So we can add these to our binomial tree. CUU is the only state with a positive payoff. It's 100. CUD is equal to 0. CDU is equal to 0. And CDD is equal to 0 as well. The only state that has a positive payoff is the up-up state, which is really, if you think about it, the only state we need to worry about calculating a risk-neutral probability for in the computations. Hey, but regardless, in part 2, we're going to calculate out all the risk-neutral probabilities. The risk-neutral probability of moving up once is equal to QU. Risk-neutral probability of moving down between 0 and little t is 1 minus QU. Risk-neutral probability of moving up twice in a row is equal to QUU. Up then down, QUD, QDU, and QDD. Okay. Risk-neutral probability of moving up once is given by the formula. It's e to the r times little t minus d over u minus d. Okay, very similar to our formula in lecture 12. It's equal to e to the 0.00 times 1 minus 1 half over 2 minus 1 half. This is negative, or whoops, it is 1 minus 1 half over 2 minus 1 half, okay, which is going to be 1 half over 3 halves, or 1/3. This is going to imply that QD, 1 minus QU, is equal to 2/3. Okay. So what we want to do is we want to get the risk-neutral probabilities of the terminal states. The intermediate states are not really of interest to us. Risk-neutral probability of the up-up state is the probability of moving up twice in a row, where the conditional probability of moving up at state U or D is the same as a single movement at date 0. Risk-neutral probability of moving up 2 times in a row is equal to QU times QU, or 1/3 squared, equal to 1/9. Risk-neutral probability of moving up once, then down, is equal to the probability of moving up first, and the probability of moving down next, equal to 1/3 times 2/3, equal to 2/9. Risk-neutral probability of moving down then up is equal to the probability of moving down first, multiplied by the probability of moving up next, or 2/3 times 1/3, equal to 2/9. And the risk-neutral probability of moving down twice, you could just take 1 minus the sum of all these. You're going to see it's 4/9. Or you could say it's 1 minus QU, probability of moving down once, multiplied by the probability of moving down again, equal to 2/3 squared, or 4/9. Okay. We now have all the inputs we need for the FTAP. The FTAP tells us in part 3, so in part 3 we want to price the call option now, right? So in part 3, we price the call option using the FTAP, e to the negative r dot t times EQ of xt, or CT in this case. Okay. We have that this is equal to e to the negative rt. In this particular form, the expectation is going to take, always remember, it's just a weighted average of the payoffs times the probability of each of those states. It's going to be the weighted average of QUU dot XUU plus QUD dot XUD plus QDU dot XDU plus QDD dot XDD. Okay, plug in our inputs. Risk-free rate is 0% times capital T, which is 2. QUU is 1/9. Payoff in this state is 300. All the other payoffs are 0, so you could effectively just ignore them, but we'll just write it out for completeness. Sorry, I should be more specific here. X is correct, but we're really interested in the call option, right? Yeah. Okay. Plus QUD is equal to what? It's equal to 2/9 times the payoff is 0. Okay, we just go back in these two slides. We'll see that. Probability of moving down then up is 2/9. Payoff of moving down then up is 0. Probability of moving down twice is 4/9 times 0, 0. Okay, and so this is going to equal 1/9 times 300. Check my math. Okay, and so this is going to be equal to 1/3 times 100, or equal to 33 1/3. So the call price in this two-period model is $33 1/3. Okay, so that wraps up the first part of lecture 13. We learned about pricing in the two-period binomial model. Let's take a quick break and we'll see we can just generalize this to any number of periods. 2 is not special at all. Okay, so we'll resume after the break.